In the last class, we have started discussing some algorithm design techniques, and we discussed the concept of balancing, where the recursive split was balanced to obtain the optimal structure, and there we studied how to minimize the complexity of that balancing. And today we will discuss another issue, and that issue is related to solving of identical subproblems, and it leads to the concept of dynamic programming, and we shall pick it up with a traditional example and the old one, which is the problem of solving Fibonacci numbers. We have already seen that in order to solve Fibonacci numbers, you have got the recursive equation is like this. The program is fib n if n is equal to 0, we returned 0. If n is equal to 1, return 1, and otherwise we can return fib n minus 1 plus fib of n minus 2. This is the recursive definition of the problem, and in order to analyze whether this program is good or not, we will have to, like in the split we tried to open up the recursive structure and see which one was most optimal. Here again we will open up the recursive structure. In order to analyze any such program, you will have to open up the structure. So let us see, let us solve it for a 5. So to solve fib 5, you have to solve 4 and 3. And recursively, you will first solve 4 and then 3. So you will come to solve 4, for that you will solve 3, and then obviously after 3 you will come to 2. You will come here, you will solve 2, then you will solve 1. Then for 2, you will solve 1 and 0. 1 is a base condition here, and this will return a value 1. It will come here, it will call this will return a value 0. This will add these two, and this will return here a value 1. It will come and solve this will return a value 1. It will come here, this will return 2. Similarly, it will come here, and again you will start solving this 1 to return a value 1, then come here 0, return 0, then this will combine to return 1, this will combine to return 3, it will come here and repeat all these steps, that this structure will be repeated here. The whole sequence will be repeated, and this will return 2. So this is how we will be able to solve the Fibonacci number problem. And we have also seen, we have developed a recursive equations to find out how many additions you will do. The number of additions we saw, the number of additions an is equal to 0 if n is equal to n is less than equal to 1, and it is the number of additions that you would do for n minus 1 plus the number of additions that you would do for n minus 2 plus 1 for n greater than 1, isn't it? This is what, and we solved it in some class before and saw this is possibly fib n plus 1 minus 1 or something like that. This is what it really does come to. And fib n we know is an exponential number, so this algorithm is going to take exponential time. Now in order to analyze why this algorithm does not work polynomially, is if you open this structure, the first thing that you will notice is that identical problems, subproblems are solved repeatedly. And this is what leads to this. One obviously is a base condition, so there is no question of repeating this, but 2 is going to be solved here once, and inside this also once, because this structure is there. So 2 will be solved 3 times, 3 will be solved twice, 4 and 5 will obviously be solved once only. But if you take a large number, say 100, each of these lower round numbers will be solved again and again. So this is the core problem of such solving Fibonacci numbers. So how do we get about solving such problems, get about solving identical problems repeatedly? This problem has to be circumvented. And in other situations where you come to a problem and you open up the recursive structure and see that a subproblem occurs multiple times, and because you have written it out in a recursive fashion, this subproblem is to be solved repeatedly again and again. So how do we get about, how do we circumvent this problem, and how do we resolve it? The method of doing so and solving an identical problem only once is the gross idea of dynamic programming in computer science language. Now there are various ways of looking at it. First we shall see the most general approach, and after we see the most general approach, we shall see how to adapt it to such Fibonacci numbers and how we can use this for other problems. For example, instead of given a Fibonacci sequence, somebody may have given you Fn is equal to Fn minus 1 plus say 2 into f of n minus 12, or you may be told Fn is equal to f of 2n plus f of n by 2, and you have got base conditions that this is for n greater than 1 and n less than 100, and n greater than 100 it is 0, and n less than 1, that is when n is equal to 0 it is 0, and it is 1 for n equal to 1. Even in this you may be asked to find out, and if you open this up you will see again identical subproblems will be repeating again and again. So how would you solve such recurrence equations, or in general such recursive problems where you have got identical subproblems occurring many times? So the first thing and the most obvious thing which would come to mind to solve such identical subproblems is memorizing the solutions to the subproblem solved. That is, if you have solved a subproblem already and if you remember that solution, you can just pick it up next time you come around it. So, but in order to memorize or in order to remember, so in order to remember this, you need to have some data area, and this will be a global data area which you will have to remember. So given any such problem where you have to do, and you know that you have to remember certain values, a simplest idea would be to maintain an array of those values. So let us see how we would do it here in the Fibonacci numbers problem. We would maintain two arrays. One is the array f of values, and the array done, which would a Boolean array which would indicate whether this value has already been obtained or not. So let us do two things. One is, let us maintain a value array, and let us maintain a done array. How it may be made dynamic, etc., etc., we will look at it later on. But if we maintain these two arrays, global arrays, and initialize them like this, we initialize them val 0 is equal to 0, val 1 is equal to 1, and done 0 is equal to done 1 is equal to true. say true is 1. So we initialize it like this and we write out our recursive structure again, but with a slight modification. Fib n, we need not bother about these base conditions anymore, but even if you bother about the base conditions, it does not matter. Can anybody now tell me how we will solve this problem? If done n is equal to 1, then return, yes, return val n. Otherwise, what would you do? X is equal to, recursively call it, n minus 1 plus now what else would you do? Yes, done n must be now made 1. Okay, done n now must be made 1 and val n must be made x and return. Here also you must initialize all other dones to 0, that you must maintain. All other done n is equal to 0. Now if you have done this, then let us solve fib 5. To solve 5, we first see what our val and done arrays are. Val 0 is 0, so this is val and done. It will start like this, all these will be 0. Okay. So to solve 5, you will see it is done. No. This is the array index 0, 1, 2, 3, 4, 5. Done 5 is true? No. So you will call this. So you will call 4. And after you come back from 4, you will call 3. So you will come to 4. Done is true? No. You will call 3. Then 3 you will call 2. 2 you will call 1. When you come to 1, done is true, so you will return val. So here you will return 1. Then 2 will call this part 0. When it comes into 0, again done is 1, so it will return 0. So now done 2 will be made 1 and val 2 will become 1 and it will return 1. When it comes to 3, it will call 2 again, 1 again, 2 has done, now 1, again done 1 is 1, so it returns 1. Here now at 3, it will make done 3 1, it will make val 3 2 and it will return 2. Here it will call 2, but when it comes here, it will get done 2 equal to 1, and once it gets done 2 equal to 1, it will just take val 2. Now here this will make it 1 and this val will become 3, it will return here. It will call 3, done 3 is 1, so val 3 will be returned. Val 3 is 2. Now done 5 will be made 1, value of 5 will be now become value of 4 plus 3, 5 and 8 will be returned. So this way a problem which was solved before, especially here and here, is not solved again. So the total number of additions is now limited to this, this and this. So total number of additions becomes the number of values only, but you have to make as many number of comparisons as well, and you have to have additional data to store this. So by storing this information, we have reduced the addition from exponential to order n. The comparisons have also become order n, but that's fine because the number of additions are now order n. So you have reduced the exponential time algorithm to a linear time algorithm by just remembering certain values. The same idea can be used in places like this where the range of n is known a priori. If the range of n is not known a priori, then what will you do? You will have to maintain a data structure like a linked list for storing the values which you know. And what data structure will you maintain if the range is not known a priori? Suppose you have got identical problems and you do not know the range of numbers, then what data structure will you maintain? You can maintain a linked list of values, or what do you have to find? You have to find out done n. So, and it's dynamic, you don't know which n's are actually now present. So you have to find n quickly, and when a new n is done, you have to insert n. So your operations are insert and find, and on a set of numbers. So to do insert and find on a set of numbers, which data structure will you apply? A balanced binary search tree. So this is how you see that as and when the problem comes and as the data structures are known to you, you will be using data structures for algorithm design and algorithm design for data structuring, and they go hand in hand to solve a large number of problems. So that is what I tried to say in the beginning, that algorithm and data structuring are so interlinked that they go exactly hand in hand to solve a problem, and you cannot separate one from another when you come to a particular problem. So here we have seen that to do dynamic programming in an efficient way in many situations, you will need a data structure to store that memory that we were talking about. Alright, and we have already seen that to solve many data structuring problems, you may need to solve a number of algorithm design problems. We shall come to it in subsequent classes. So this is the obvious way of solving a problem. But if you want to solve the problem in a more, there is another way of looking at it even deeper, to see exactly how much you need to remember. Do you need to remember everything? Yes or no? For that you will have to go in depth to see how the recursion proceeds and how the values are calculated. Here, though you have written them down in a top-down fashion for 5, but see how the values are calculated. 5 calls 4, it does not compute the value of 4. It calls 3, 2, 1, and the values are computed in this sequence. So the values are where the calls are made top down, the actual value computation goes bottom up. So if you have understood this definition, which was the intuitive definition of the problem, if you have understood that what I have done has to be remembered, and if you have understood in exact terms how this algorithm computes the value, you might as well throw away the whole thing and compute it yourself. So the best way to compute this is to compute it bottom up yourself now, because now we have understood how to do it. So we compute it backwards up. That is, in order to compute 5, we know we have to compute 4, we have to compute 3, we have to compute 2, and we have to compute 1. So and then we know 1 and 0. So we might as well compute from 2 backwards up, because that is the data dependency. The data dependency is obvious here, but it may not be so obvious in problems like this. In problems like this, the data dependency may not be so obvious. Only when the data dependency is not if the data dependency is not obvious, then use a done array and a val array and your problem is solved. But if you can go further and find out the data dependency, then you can work it out according to the dependency in your own way. How would you do it? Solve it bottom up. For I is equal to 2, I less than 6 or n plus 1, I plus plus. Simple. Val I depends on I minus 1 and I minus 2. And if you are solving it bottom up, you know that when you are solving val I minus 1 and I minus 2 are done. So you need not check whether they are already done. This is a simple example where this comes obviously. So in other examples where you know the structure, we will see what is the approach to be followed. But let us see here. It is like this, and the dependency structure is something like this. Now suppose your dependency structure was in some other problem. Suppose your dependency structure was like this. Then you would have had to compute it in what sequence? This one first, so you would have to do a numbering. This one first, then second you can compute this or this or this. Can you compute this second? No, because this depends on this. So you could have computed this second or this second. So this is the first which you compute, this is the second layer which you compute, this is the third layer which you compute, this is fourth, and this is last. So you need to find out the sequence of dependencies. And once you know the sequence of dependencies, you can forget about maintaining a done array, you can forget about the recursion, and you can solve it based on the dependencies itself. So you will see various versions of dynamic programming. If a person can find out the dependencies, he will simply write it in for loops, one or more for loops. In other situations where the dependency is not known, he will use a done array or a variation of that done array to remember what problem has been solved earlier and use the value itself. So dependency usage and remembering what you have already done before so as not to solve a problem repeatedly is the idea of dynamic programming. And this idea is used in several applications. I will just give you some examples of problems where these are used. Consider the problem of multiplying a set of matrices M1, now in order to multiply this 10 by 20, this must be some 20 by something, say 30, this must be some 30 by say 10, and this may be 10 by 40. Now to multiply two matrices, if we use the simple algorithm M1, suppose I multiply M1 by M2, this is, how many multiplications do I require? Multiplications are more expensive than additions. You require 10 into 20 into 30 multiplications. Alright. So to multiply two matrices like this, I require so many multiplications. Now I have got a lot of alternatives to do. Matrix multiplication is associative. I can multiply these all and then with this, or I can multiply M1 cross M2 with M3 cross M4. If I multiply this with this, I will be multiplying a 10 by 30 matrix with a 30 by 40 matrix, and here I will multiply this and this. Now depending on the sequence in which I multiply, my total number of operations will, total number of multiplications will come. If I have to find out the optimal sequence, what will I have to do? I will have to find out all possible such associative combinations. Alright. So, to solve this problem, what are my choices? To solve from M1 to M4, my choices are M1 with M1, M2 to 4, or M11 with M24, or M12 with M34, or M13 with M44, and then again 2, 4 I will have various choices, and based on these choices whichever is the minimum, that is the one I should take. And if you write out, see, therefore M14 is equal to minimum of M11 multiplied M11 multiplied by M24 plus M12 multiplied by M34, plus nahi, comma M13 multiplied by M44, and again recursively M24. M11 is 0, multiplying a matrix by itself, or if the difference is 2, you know what is the cost. Alright. So, multiplying these two will be multiplying, this is 0, 2 to 4 you can find out the optimal cost, and then this will be 10 into 20 into 40. So, this way you can set up the equations, and you will see that when you have a large one, M1 say 10, then you will have multiple occurrences of M say 25 will occur in many places in the recursion. If you draw up the full recursion tree, you will see a lot of identical subproblems coming up, and this is a problem which is a very clear candidate for dynamic programming. So, such problems, there are various other problems which are candidates for dynamic programming, which comes up when the opening up of the recursion leads to several identical subproblems to be solved, and all of them can be solved by various grades of approaches. The approaches are, firstly you will have to remember the problem that you have solved before. Secondly, you have to see whether you yourself can find out the dependencies. If you can find out the dependencies, then you can forget about the done array and just work it out in a loop. And if you cannot find out the dependencies, then simply use the done array and use the recursion. At least your number of repeated problems, subproblems which are identical will not be solved repeatedly. You will be requiring some extra space, that's all. So, dynamic programming, to conclude, is a very essential component of algorithm design, like balancing, which tries to optimize the recursion split or the way in which we decompose the subproblem. Dynamic programming tries to ensure that identical subproblems are not solved multiple times. Therefore, dynamic programming, like balancing, is another very, very important aspect of algorithm design, and it comes into play in many cases, and both in many situations you will see the combination of balancing and dynamic programming coming into the picture.